All right, on the board is today's attendance question. So suppose we have a loan that follows simple interest. We want to calculate the future value for the $3,200. So it's a calculation of a value in 3 years. Thank you. Thank you. As we mentioned before, we try to use a model to figure out how money is growing. In this one, we have a simple interest model. So we're assuming it's initial investment multiple. We're using K. Most of the textbook for finances use P for the principal, but in this book, we're using K. The growth factor is the growing fraction. The growth factor can be, it's being called accumulation function in the book. The growth factor can be a linear function or a exponential function. So we're assuming it's simple interest. So it's a linear function. Original factor is 1. 1 plus ST is the model that we're talking about in 1.4. Right, in this question, we try to identify the value in this question. The K is the original investment. It's 3,200. Let me try to get out of the way. So it's not in the way. Okay, K is 3,200, and we have the interest rate, which normally is being called I or R, or this is simple interest. Let's use S. S is equal to 0.08. I try to make the notation match the notation in the book. And another thing is the time. And time is normally noted by number of years. In this question, it's 3. So we put in everything, the calculation for the value at time 3, which is 3 years at maturity. So A3 is equal to original investment, 3,200 multiplied by 1 plus 0.08 times 3, and time is 3. And that will be the calculation. So what you can follow for calculating its future value. Let me go back to the page. Okay, thank you. Okay, so the final answer is 3,968. All right, any question for 1.4? There's a assignment on web work for 1.4. Did you guys get to do it? I feel like I only see two students that did most of it, so I guess you haven't really started. Did you start the homework?
No, I just, the bar computers that we got,
Uh-huh.
I finally just got mine set up last night, so
Oh, okay.
I haven't got to.
Melanie,
Yeah, I haven't started yet, but
okay. Okay, and we tried a few questions last time when we was looking at solution. Coding. All right, this is, I tried the first question, second question, I guess I also tried the number 5. And also, I was trying number 10 right before class. If you run into any problem as we're going through the homework, please let me know. The first assignment is simple interest model. It followed the formula that we were using for this question. It's an attendance question today. So we shouldn't have a lot of issue with it if we go through it. Tyler, do you have any questions? Are you okay?
Yeah.
All right, did you start the web work homework?
I have not yet.
Oh, okay. That's the calculation for this question. Next question. Do you want to calculate it so we can submit it? It's a simple interest question. That's section 1.4 that we're doing. Thank you. Answer is B. All right, so for today, we're gonna try to continue where we left. Okay, this is where we left. We set up a model for the simple interest example. Accumulation function for simple interest accumulation is 1 plus ST, where the S is simple interest rate, the T is time, and we try to count the time at years. T is number of years. And so here, being able to accurately calculate time is very important. K is the original principal value. All right, so today let's talk about 3 different ways to calculate time. You want to make sure it's accurate to days. And how many days from the beginning of the investment to the ending of the time is also very important. So we have 3 different examples. The first one is called exact simple interest. Basically, the denominator is the actual number of days in a year. The numerator is the actual number of days in your investment period. So let's look at example. Brad borrows 5,000 from Julio on October 14th, 1998 at 8% exact simple interest. Agreed to repay the loan in May 7, 1999. So we want to find out how much, what's the amount of payment using the exact simple interest. So by the time the loan is due, he had to pay back the 5,000 plus the interest. So here's the thing, how do we calculate the interest? So according to we mentioned earlier, the interest should be S times T. The interest ratio should be S times T, but exactly what is that time? And that's the problem in here. So you can see this is not a whole year. If it's entire year, it will be October 1998 to October 1999, but it's October 1998 to May 1999. So it's less than a year. So we need to find out exactly how many days. In the first example, we're going to do exact number of days and exact number of days in a year. The exact number of days in the whole year is 365. So the denominator is 365 for the mentioned the time. So we're going to try to derive that fraction. Basically, the word actual is how do we find out the exact time? It's gonna be less than 1, but we don't find the actual time. So here's the actual calculation. You can see it's kind of lengthy. If you truly want to find out how many time, what is the date? Original date is October 14th. So in October, 14 day has passed. So how many days is October? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So October has 31 days. The calculation, you go 31 days, and then 14 day has passed. So you have 31 minus 14. And in November, there's 30 days, December 31 days, January 31, February 28, and so on. You can see we are calculating exactly how many days, exact and any months. That's what's making it a little bit lengthy for the computation. And it ended on May 7th. So in the May next year, there's 7 days in that day. So we are counted all the days involved in the investment period, and it altogether is 205. So the actual time is 205 divided by 365. That's really the calculation for time. Everything else follow the K time 1 plus ST. The K is 5,000. That's the original principle. This is the 1 plus ST, and T is the one we spend so much time counting. That's when everything's calculated, we have 5,224.66. Any question for this example? Okay. So we're trying to derive a different way to calculate the time. All right, second method, we are trying to uniform how we count how many days in each month. Instead of finding out exactly how many days in each month, we assume the entire year has 360 days. We assume the number of days at every month is 30. Okay, let's try to streamline the calculation so we don't have to count month by month. So back to that question that we had earlier, the calculation of number of days in the investment period become, here's the calculation. So you're gonna 360 multiplied by year 2 minus year 1. So this allows you to figure out number of years, how many whole number of years has passed. And then you're going to take 30 times the second month, the ending month, minus the beginning month. So here's ending year minus beginning year, ending of the month minus beginning of the month, and this is the ending day minus beginning of the day. So look at the question. We started with 1998, ended with 1999. So this is 1999 minus 1998. For the months, we started with October, ended with May. So here it's going to be 5 minus 10, May minus October. And the number of days will be, we started with October 14, ended with May 7. So 7 minus 14. So then in those subtraction, we're allowing some of them to be negative because this one is positive, right? We really don't have 360 days. So that 360 times 1 is a lot. And you start seeing some negative, and then subtract out some of the days. So this calculation is called ordinary simple interest. It has a more systematic way for the calculation. I gave you a faster way for the calculation, so we don't have to worry about each month how many days. So here's a calculation for the one that started with October 14, 1998, ended with May 7, 1999. So here's the calculation of days. 360 is number of years. There's 1 year passed, and 5 and 7 are the ending months and beginning months. We subtract, and there is negative 5 months. 7 minus 14, there's negative days. Altogether, we end up having 203. So it's really not that much, right? The exact days was 205, and then we use this ordinary simple interest calculation. We end up having 203. So we didn't really lose that much of a value in this computation. Any question? All right, so with this calculation following the same K time 1 plus ST, we end up having a final payment of 5,225.56. If we compare, the difference is about $1. So it looks like almost equivalent in between the two calculation. Any question? Are you okay? Easy enough to understand? Are you okay? All right. There's one more. Okay, this is called the Banker's rule. So this rule actually is giving us more interest to the customer in this computation. We're not doing actual or 630, 360. We did actual over 360. So in this computation, we're going to use the exact days, but we're not assuming the entire year has 365 days. We're assuming 360 days. Okay. It depends to whose advantage is this. If you're talking about loan, you're paying back. I guess that's the banker's advantage, right? If you use this, the exact days is 205, which was calculated in the first case, 205 divided by 360, and then you have at least $2 more that you have to pay back to the bank. So that's the answer to this season. It's really about the numerator and denominator, those two, right? The exact would be 205 over 65. If you have the 30 over 360, you have 203 over 360. But if you have the exact over 360, this fraction ends up being a little bit bigger, and we have to pay more. If it's about loan payment, I think it's to the bank's advantage in this rule. Banker's rule. Any question? Okay. So this is some detail in the simple interest calculation. Most of the time we don't even worry about it, but we can specifically this. All right, so we're moving on to 1.5. I have already assigned 1.5 homework. 1.5 is called compound interest. Even though it's new, but I believe most of us have a little bit of experience with compound interest. So here we are. So in compound interest, we assume the accumulation function take this form. Here is the accumulation function in compound interest, meaning that the interest is being compounded based on how frequent we're compounding the interest into the principal. Okay, so here the I is representing the interest rate. And K, of course, should be it should be the number of years. Should be. Any question? So that's the compound interest model. If you remember, the normal formula for compound interest is P times 1 plus I to K. But in our case, we use a capital K for the principal. It's okay. Okay, a couple of special things we want to talk about. Number one is, mathematically, any number to the power 0 equals 1. And also for a higher number, for a bigger positive integer. And since we have AK equal 1 plus I to the K power, that's what's been defined in the previous claim. We're proving the claim. Okay, let's try to rewrite the claim. Says that if the accumulation function AT has associated periodic interest rate in all equal constant, then AK should be in this formula. So we're trying to reaffirming earlier what we're talking about. And when you have a simple interest, we have the I1, I2, I3. I think we calculated one of the examples. We proved that they are not the same. The interest rate for every time period is not the same. In this example, we got calculate A1, I2, I3. For simple interest, the I1 equal to the original simple interest, the 5%. And it gets slowly lower as time goes on, right? This was the example that we practiced before, but we're hoping for a model when every time period, the I is equal to the same thing. And this is one of the discussion we're talking about notation. I1 is the interest rate for the time interval 0 to 1. IN is for the interval from n minus 1 to n. And T1, T2 is the interest rate from T1 to T2. Right, so this is, in this definition, we have this under the underlying idea is that maybe all these I are not the same I. Now, for the compound interest model, we have any equal interval, they will have identical interest rate. And that's true for the compound interest example. And this is what we're trying to prove over here, saying if the accumulation function has a periodic interest rate and they're all equal to a constant number I, then the accumulation function would be this. Right? And then the following proof is trying to verify this. And we're trying to look at the interest rate for all time period. So we want to show that the for the case, if it's for the case time interval, then for k+1, the interval, the interest rate is still equal to I. So here's a proof. If you want to try to calculate I k+1, what you have to do is the time interval from k to k+1. K to k+1. Right, so the beginning time is k, the ending time is k+1. Here is k+1, and then k-1. We're assuming that at all the time before k, the interest rate all equal to I. And here we're trying to prove that between k to k+1, the interest rate is ik, it also equal to I. So we're going to prove that if the accumulation function equal to 1 plus I to k, then it would be the case. So here's a proof. AK is 1 plus I to the power k, and AK+1 is the one we're trying to determine. If it's equal to I, then AK+1 is supposed to follow the same formula. So that is equal to I, and you're going to multiply the denominator with the I to the left, and then adding to this part, and then over here, all these calculations, verify AK+1 does equal to 1 plus I to the power k+1. So that's just trying to verify that over that time period, the interest rate is still I. Any question? Right, so we're trying to make a statement saying that if you want for every the same interval, you should have the same interest rate if it's a compound interest. And which is why it's the preferred accumulation function. And for the rest of the chapter, we actually use the compound interest model as a persistent way to model the growth of money. And that's why simple interests are being only applied for shorter term loan. Okay, so instead of AK equal to 1 plus I to the power k, now here we're using AT equal to 1 plus I to the power t. In this case, a t can be any number, any positive number. It doesn't have to be integer anymore. Why do we use k before? Because we can use induction. If you want to do mathematical induction, we're assuming the k is an integer. We're proving that AK equal to 1 plus I to the power k for all positive integer. In the sense that it's okay to apply mathematical induction. But over here, we're generalizing the formula for compound interest for any time. So the time t here can be integer or any part, like could be 1.2 or 1.23, so it have to be integer. Any question for the interest model? So this is a accumulation function. All right, so a comparison graph between the two interest model, the two accumulation model. If the accumulation function is simple interest, you see a straight line starting from 1. If you have a compound interest model, it's 1 plus I to the power t. So when the t equal to 0, 1 plus I to the power 0 still equal to 1. So either way, accumulation function always start with 1 because that's the $1 that we're talking about. AT representing the gross of money when the original money is $1. And capital A was having the original principal being the K dollar. So, and we want to study how $1 are growing before we can study however amount money is growing. All right, so let's look at example, to apply compound interest for certain purposes. Okay, this question, we're assuming that we have a deposit of 12,000 in an account where a grow according to a compound interest accumulation function. So 1.05 to the power t, that means the interest rate is 5%. So he makes no further deposit and or withdraw until he closes account 6.5 years after he opened it. How much money does Fernando receive when he closes the account? So basically, we're trying to find eventually what he has after 6.5 years. So the calculation, I wonder if I put it in there, no? All right, so we're gonna try to calculate it ourselves. Well, the solution is in the book, but we're just treating it as a little exercise. So essentially, we are following the calculation of future value. You remember, change color. The amount of money it has in the account is AT, which also equal A times the lowercase at. The amount he has originally is 12000, and then the interest rate follow the 1 plus the 1.05 to the power t. The t should be the time. In this question, the time is 6.5 years. So 6.5 will be the time. So that will be the calculation for how much money he has in 6 years. So we would try to use a calculator on this. The final answer would be right, 1.5 to the power times 1.05 to the power of 6.5. So that's the final amount. Any question? Are you okay? Yeah. So the interest is roughly that much. That's a lot higher than $12,000. Sorry if I made a mistake with 6 years. Let me calculate if it's a simple interest, what do we have? 1 plus the interest rate is 0.05. If it's simple interest, it would be still not less. Right? This is a simple interest model. The compound interest model would be back to the power of 25. So it kind of makes sense. You guys have the book. Okay, it should be the same amount that you see next week. Pull out the textbook example practice. So that is our first example on compound interest. Any question? All right, let's try one more example. So this one is called a tiered investment account. So basically, this is promoting to have more money saved. So it says that if the amount is less than, if the money is less than 2,000, then the interest will be 2%. If the money grow past 2,000, I mean, as you save more money, there's interest rates which causes money to grow. So if it grows and it become the value between 2,000 and 5,000, the interest is 3%. Okay, and then if it's 5,000 or more, then the interest is 4%. Okay, so that you can see as money growing, interests get more. So the more you save, the more interest you have, kind of earning your money from your investment. So here's a question: if a person saves with 1,800. All right, so that will be 100 1,800 T. Want to find out. Okay, this is a different than, so this is the one, the principle is changing. So it kind of goes against our original perception is original money time AT. In this question, because your AT is your principal is changing, interest rate is changing, therefore, yes. So it's different than having the 1,800 times AT. Right, so if you want to show it's different, then first you have to set up the amount function properly. So here we do this. So we have to find out when does it go past the. I guess it's not copy the questions. I do need the space to write it. So let's see how it does. Okay, so if we set up the timeline and at time 0, we have a amount that was 1,800. And there's a time when we don't know what's the time, so let me just call that T1. There's a time when the amount become 2,000, right? But between 0 and T1, the interest rate is 2%. And then it start growing at a time, let's call that T2, and the quantity of money grow to the balance grow to 5,000. This is a balance, not the change. And the interest rates in between T1 T2 is 3%. And then after that is 4%. So there's a slight problem to the whole model. We don't know T1, T2, so we can't really model the investment. So if you try to write your function AT, okay, so originally it was like this is 1,800 times 1.02 to the power T. Okay, that's before T turn T1, and we're gonna find the T1. Okay, so let's first calculate that. That's when the growing of the money reaches the 2,000. We gotta determine the T. So here is a calculation. Before T reached T1, it followed this growth function. So we want to find out what time does this money grow into 1.02, grow into 2,000. So then we can determine T1. So this is a try to determine T1. It's a process. Feel like I have no space. All right, so in this calculation, what we're gonna do, we're gonna solve for the T. That's how you can solve T1. Are we okay so far? We need to figure out the T1. Like since when is the money reached 2,000? And that's when we are changing our interest rate. We need to know that time. So we divide both sides by the 1,800, and then we can have 1.02 T that essentially equal, we divided the 18, essentially it's 20 divided by 18. Right, and then to solve for the T, we take a natural log of that equation. So we have natural log of 1.02 times T, take natural log of the left side and take natural log of the right side, 20 over 18. Natural log, and to solve for the T is going to be a division, natural log of 20 over 18 over natural log of 1.02. Oh, I gotta know that time. Let's see, this is natural log of 20 over 18 divided by natural log of 1.02. The time 18 to time is 5.32. I'll assume this is 5.32. Are we okay so far? Yes. Okay. So by the time of 5.32, that's when we have 2,000. So since then, they start growing with a 3% interest rate. So how does it grow after that? We're gonna look at the formula. It's gonna based on the 2,000. So you're gonna have 2,000 times 1.03. Right, that's how it grows. But then you have to look at the time. If it's follow 1.03 after the T1, then whatever the time is, you have to subtract that time, right? So it's gonna be the time past that time is T minus 5.32. So this is when T is bigger than 5.32, but less than whatever that time is. We're gonna find out this time. Okay, any question? Is it okay? Have any concerns, any problems? Are we okay? So it's that at T1, you already have 2,000. You're letting it increase from that time. And that's why I think the time should subtract the 5.32 as a time. All right, and then we're probably gonna follow similar logic, and we have to find out what time does it reach 5,000. So you're gonna have to take that increase function and let it equal to. So you're gonna have 2,000 times 1.03 to the power of T minus 5.32. Which is equal to 5,000. We're gonna find out when does it reach 5,000. So then the 1.03 to the power, yes, to the power T minus 5.32, which equal to 55/2. 5,000 divided by 2,000, which is essentially 2.5. So you take natural log of both sides of the equation, then T minus 5.32 would equal to natural log of 2.5 divided by natural log of 1.03. And then the final T is going to be add 5.32 to both sides of the equation. So let me try to find it. So it's gonna be 5.32 plus natural log of 2.5 divided by natural log of 1.03. So we get that is the time. And it's roughly 36.32. So it's 36.32. Just like 36 years later when it reaches 4,000. Are we okay so far? Next, then starting T2. Starting T2 is now $5,000 that we have. It's our balance. So now it's going to be 5,000 as your principal. It's growing at an interest rate of 1.04. To the power of T minus, you're going to start counting your time because that's your beginning time, minus the 36.32. This is for the time bigger than 36.32. This is going to be our accumulated amount function, the amount of money in the account. Any question? It's a little bit more complicated. We look at the piecewise defined function because the interest rate is different. Any question? Here, because we're changing it. Also, because there is this uncertainty about what time are you reaching a certain amount. And this is what I hated. Sometimes the bank is using that rule. You got to reach certain amount. This is what kind of balance you have, what kind of benefit. But before you reach that, you never know. Like they change our mortgage insurance, if you have to reach certain 80% of your principal, then they will revoke the mortgage insurance. Certain things happen when the balance reach certain point. We don't, in real life, we don't normally go in this to sit down do the calculation, figure out whether they reach certain amount. So you let the system itself to determine the timing. Okay, anyway, any question for the computation? So we're solving exponential equation just because we need to know the time. And the time is in the exponent for the accumulation function. It's this example. You can see that we don't always see k time at. Here we're saying that this accumulation function, this amount function is different than k time accumulation function. So it doesn't always follow. All right. Okay, let's talk about interest rate. As you can see, interest rate change. The bank prefer us to have more money saved. That's why they kind of offer different interest rate for different person. That's why I'm guessing those billionaires actually have a better interest rate than our regular day-to-day person. But what factor affects interest rate? Okay, so there's a lot of things affect the interest rate. Interest or financial product are like merchandise. They are also follow supply and demand relation. So if there's more supply, the price will go down. If there's more demand, the price will go up. Okay, so what kind of policy affects it? Two of the manufacturers. Who's the one determining the interest rate? The government. Okay, there are two common factors. One is the physical policy, and the other one is monetary policy. A physical policy such as spending and taxation. Basically, when the spending go up, interest go down. When the tax go up, interest go up. A monetary policy refers to the regulation of the money supply and interest rate by the central bank. So this is exactly how much money do we actually have. That also affects interest rate. Any question? We're certainly not going to be quizzed over this, but it affects how we look at things. If we're having any financial problem that we consider. Right, so there's a couple of other examples in my 1.5 about compound interest. This one is the easier version of the changing interest rate. So here we're saying that if you save $8,000, the first 3 years interest rate is 5%, and then the next 2 years is 5.5, and the following 4 years is 6%. So this is recommending for people to save their money for a longer time. The previous example is recommending or motivating people to save more money. So if you're trying to get people to save more money, you offer more interest rate when the balance is high. Now, this one, we offer higher interest rate when the money is being saved for a longer time. But here, the first 5 years, the first 3 years is 5%, next 2 years is 5.5, and the following 4 years, 6%. So we're gonna find out what happened after 9 years. Basically, all these years, you're gonna try to calculate it. I don't have a solution in here, so let's look at how we calculate this. Again, you can always verify your calculation or my calculation when you're reading the book, and pretty much are using the textbook example as example to practice over the compound interest. All right, so the question says we are looking, if you're trying to study or figure out what was going on, the best way would be have a timeline. And in this case, starting from time 0. And then we can see the first 3 years. So at time 3, between 0 and 3, this is 3-time interval. The interest rate is 5%. Right, from then the next 2 years, so 3 to 5, between these 2 years, the interest rate is 5.5%. And then the following 4 years is 6%. So 4 years, so that would be time 9. At time 9, between 4 and 9, the interest rate is 6%. So that drawn timeline kind of clarify numerical information allows you to study it in a better way. But there's no cash flow. All we have is $8,000 at the beginning, and we see how it's growing. The first 3 years is 0.5, so 1.05 will be the current year growth factor. You raise it to the power 3 since it's run for 3 years. And then after that is 1.055. All these money, this is how much you have by the end of the 3 years. So it become the principal for the following years. So having that, you will raise that, multiply it to 1.05 to the power 2, so 2 years. And after that, we have 1.06 interest rate at 6%. You raise this to the power 4. So that's the growth of money in all 9 years. And that's the actual calculation for this one. So it still applied that the K times 1 plus I to the power T, and then 1 plus I to another power T, and then 1 plus I to another power T. But the growing is being in different time frame. Any question? Okay. We can definitely put that into a calculator and check out our calculation. And you can confirm this when you look at your computer. And this, we have the textbook, Georgia Field Account. 3 and then 1.055 to the power 2. And then 1.06 to the power 4. So I have a total see if it's 8,000. Okay, I was using the wrong principal. Okay. So we have so $8,000 has been growing a lot. So you can see for compound interest, even 5% interest rate is a pretty high interest rate. That was 5,000 more than the original investment. This is that exactly. But this is a long time. 9 years is a long time for investment. Okay, so this is a question about unknowing interest rate. So here we say Pedro wishes to have 12,000 in 3 years, so he can buy his father's car. Pedro have 9,800 to invest in the 3 years certificate deposit. Save money for 3 years. What annual interest rate must the CD earn? So it will have the redemption value of 12,000. So CD is certificate of deposit, which means we have a fixed interest rate and fixed term. So this is a question when we're not given the interest rate, we're figuring out what interest rate will serve your investment purpose. We have the original value, we have the future value. So then solving for the I think it's also an exponential equation. So I'm going to try to label the quantity and see how we can approach this question. Use some algebra. So we wanted the 9,800 to grow into 12,000. In order for that growth to happen, we need to know the appropriate interest rate. So our original model is like this. We have a T equal to K times 1 plus I to the power T. Okay, so if you think of which part of these numbers belong to which part, the 9,800 will be the K, the I, we don't know it, so we were supposed to solve it. The T, in this case, it was a 3-year investment, so the T equal to 3. AT is the final amount that you needed, so AT is the 12,000. So we kind of use the compound interest model as our way to set up the equation. So this is going to be 1, 2, 0, 0, 0. The K is 9, 8, 0, 0. And we don't know the I, we're trying to determine it. The T equals 3 because it's a 3-year CD. All right, so then you can see now we got equation. We can solve for the I. The first thing we'll be dividing out the 9,800. We'll have a 120 over 98, which equal 1 plus I to the power 3. We have to take the cube root of both side equations, so we're gonna have 1 plus I equal to 120 over 98 raised to the power. Cube root shows 1/3 power, right? And of course the I would equal to 120 over 98 raised to the power of 1/3 minus 1. I think that will be the interest rate. You want to make it into a percentage. Any question for the computation? I don't have the answer, so I'm gonna try to put it into a calculator and see the final answer. So it's 120 over 98 raised to the power of 1/3. And that minus 1, our interest rate. So it's roughly 7%. 6.98% interest rate. Any question? You can also double check in the text and see what was the solution of it, and just put the question up so you can follow through. All right, so that's the, what did I do? Okay, that's the last example for 1.5. 1.5 is not too complex. It follows many of the exercise we might have or sectional finance in company growth. So hope this provides enough example for us to finish 1.5. Any question? We can try some of the example on Whiteboard. I know that the wording of these questions might not be identical. You can also look at the actuarial science websites. And again, the wording there might not be identical, but we kind of have to see through how it's being stated and figure out which model is appropriate. What we're learning is just by providing the tool of the way to handle this question. Let's try the first question. Right, says investment of $4,000 at time 0 is key measured in years. So this is how the question is being stated. If the investment grows by $30 per year, find a formula for the value. And B, if the investment grows by 13% per year, find a formula for the value. So it's value at time t. Right, so the first one that we provide a linear model for the gross of money that doesn't really follow our reasoning for the simple interest. It says exact dollar amount, so it fixes the interest amount. So 4,000. We can calculate the simple interest rate, but for now, it's $130 per year. So $130 times the number of year would be how money growing because it's a linear model. And that will be my conception for the first question. It didn't provide the interest rate, so I didn't really do the interest rate calculation. Any questions? I mean, $130 per year. So 130 multiplied by the number of year will be how much money is growing out of the 4,000. Be okay. Second one. So it's 13% a year. So that means every year it becomes the previous 1.13 to the power t, I guess. So the first one, Part A is a simple interest model, and part B is a compound interest model where the interest rate is 13%. That's the first example in the white paper. So you can see the wording, and sometimes mentions simple interest or compound interest, but a lot of time it doesn't tell you what model are we supposed to use. We often have to determine for ourselves what's going on, what will be the mathematical formula for it. Okay, so this is the second question. All right, it says what annual rate of interest compounded annually is required to double an investment in 7 years? So this question. Right, so keyword is double, meaning that original way you're we're just talking about the AT, right? The AT. We don't know how much money do we have originally. If you originally have $1, now you have $2 in 7 years. So at time 0, you have $1. At time 7, you have $2. Right, and then it's just a compound interest. So what's compound interest is 1 plus I to the power t. That's a compound interest model. We just need to find out the I. According to what we are writing here, at time 0 is 1. That's AT. At time 7, it doubles, so it's 2 at 7. So essentially, we need A7. The accumulation function at 7 is 2. That's what I mean. So we have a 2 when 1 plus I is being raised to the power 7. And from that equation, we were supposed to solve for the I. The first thing we want to do is to remove the power 7. We'll do a fractional power. So you have 2 to the power 1 over 7. You take 1 over 7 power goes out of the equation, then clear the 7 power on the right side. And then I would equal to 2 to the 1 7 power minus 1. So that should be the interest rate we're using. But you're going to see a decimal answer. You have to multiply 100 to make it ready. So the whole calculation is this. Doubles, that's why we have 7 over 2. 2 is over double, and then minus 1. And then we're going to have to turn this into a percent. That's why I got to multiply 100. So the final answer would be roughly 10.4%. That's the process calculation. Any question? That's the question 2. I want to try the rest. Okay, this question. APR, what is APR? Is effective percentage rate, I guess. Basically, it's annual interest rate, annual effective interest rate. If the bank pays APR of 8%, so that's really our interest rate, how much should be deposited now to have 1,500 in 6 years? Second question will be in 3 years. So understandably, if you want the money faster, you have to have a higher interest rate. So question part B will have a higher interest rate. Part A probably have a slightly lower interest rate. So how do I exactly calculate it? The process is similar to what we did for the previous question. I'll just solve the first half of the question. Right, so this is our timeline. At time 0, we have, should we put at time 0, we don't know. That was a question. And we wanted to have 6 years at time 6 and have 1,500. So we wanted to have a 6 to equal to 1,500. And we know the interest formula is compound interest. We have AT equal to, let's call that K K times 1 plus, the interest rate is 8%, was 1 plus I, and I is equal to 0.08 to the power t. So that's our accumulation function. And in this case, this is a t equal to 6 years. So you set up the equation, it goes like 1, 5, 0, 0. In 6 years, we have 1,500 and K times 1.08 to the power 6. So on the right side of the equation is the amount function K times the accumulation function. Accumulation function is 1.08 to the power 6. On the left side of the equation is the actual value that we wanted in 6 years. Okay. So again, you solve this equation for K, and that will be 1,500 divided by 1.08 to the power 6. That's the amount that we have. Any question? Okay, so the solution, you can see that K is can solve by a division to find the K value. So K here is 1500 divided by 1.08 to the power 6. And you would suppose to use a calculator to find it out, but I have here. The same calculation would work for the second one, except it's 3 years. So you're gonna need more money if the growth factor is smaller. So these two are similar. Once you figure out the answer for one, the answer for the second one is pretty much comparable. Any question? All right, I'll leave the 1.5 here. Let's talk a little bit about 1.6. Okay, 1.6 is called interest in advance, meaning that we will pay the interest at time 0. We only pay the principal when the time is up for the repayment. And it's also called effective discount rate. So it's kind of like looking at money in a different perspective. And why do we talk about discount rate? Because sometimes we want to know the present value of things. Turn this off. Scan messages. All right, when money is borrowed with interest due before the money is released, we describe the relation using a discount rate. If an investor lent K for one basic period at discount rate D, then the borrower will have to pay K times D in order to receive the use of K. Instead of having the use of an extra K, the borrower only have the use of an extra K minus KD. So here the D, which is being called the discount rate. The quantity K times D is called the amount of discount for the loan. All right, I guess the easier way to look at things is to draw the timeline for what's happening here. Right, so if you think of it, it's kind of like having to pay the interest before you're receiving the money. So at time 0, and this is when the time is up, I guess it's a future time t. The discount rate is given at first, and you are trying to borrow K dollar, but you're gonna try to pay the discount first. So if you want to borrow K dollar, in this case, you borrow K, but you're paying K times D. So the actual money you have is 1 minus D times K. So essentially what you have, if you're trying to borrow K dollar, but you actually get K minus KD. The K times D is the discount. D is a discount rate. K will be what you intended to borrow. So that means that I want to borrow 1,000, but what I actually get here is 970. So that extra $30 less is assume the interest or the discount I'm paying right now. But then in the future, you're gonna actually pay the K. So if you're trying to borrow $1,000, you're paying $1,000 in the future. That's kind of, you see the money is still growing. You're getting the 970, but then in the future you're paying 1,000. It's kind of like having this much money grow into the $1,000, if that's true. I hope that if we're getting the sense. So we still see an increase of value. K minus KD is the value, the present value, and then K itself is a future value, which is slightly higher than that, of course, because you already paid the discount at first, right? So the discount rate is not the same as interest rate, but it has a similar, it serves similar purposes. Is the difference between the future value and present value. Because you're receiving K minus KD at time 0, but you're paying K at time in the future. So the differences between future value, which is K, and present value, which is K minus KD, the difference is K times D, which is essentially the interest. So you're basically paying the interest at time 0 instead of at time t. Any question? So we're looking at things a little slightly differently. Let's see. So for example, so maybe numerical example makes more sense. Suppose the person borrowed $1,000 at a discount rate of 7%. 1,000 times 7% is $70. How much extra money does he have? And so he borrowing $1,000, but he has to pay the discount immediately, right after he got that $1,000. So at time 0, he borrowed $1,000, and immediately he was asked to pay that $70. So essentially, he receiving $930 at time 0. And that's really what our answer. So the answer to the question, the extra money he can use is $930 instead of 1,000. Even though the name that he said he borrowed 1,000, he actually only had $930. Any question? So a little bit less, but you have less money at time 0. You also have less money to pay. So at time when time's up, you will pay back the 1,000 that he supposedly borrowed because he already paid the interest ahead of time. So then there's no extra interest to pay. So there's a benefit to this reasoning in the sense it's clear what you were supposed to pay. There's no change because you already paid the interest at time 0. So. But if you pay interest in the future, it's possible that the interest rate change and you might be at a disadvantage. But then again, if you have a fixed interest rate agreement, that will be a problem. So in this sense, paying now or paying in the future has pretty much the same. Okay, so let's look at effective discount rates, and we have to explain. We're using letter D for discount rate. We use letter I for interest rate because the interests are with letter I, discounts are with the letter D. So we have to mention the difference between the two. What's the discount rate? According to what we mentioned before, you have $930 at time 0. You have 1,000 in the future. So what's your interest rate? You will find the difference between the two. 1,000 minus 930 is 70. 70 is the actual interest. But if you are calculating discount rates, the actual money, which is a discount, the discount and the interest, it's the same thing. But the difference is in the denominator. If you want to find the discount rate, you divide the 70 by the 1,000, which is the end value of the entire gross money growth function. So 70 divided by 1,000, so your interest rate is 7%. So in a sense, the discount rate should be calculated by future value minus present value, provide your interest. Interest divided by a future value is your discount rate. But what is interest rate? Interest rate is future value minus present value divided by present value, right? So that's the difference. Denominator, in this case, with discount rate divided by 82, But in interest rate, in 82 minus 81 divided by 81, that's the interest rate. So I hope we're clear what's the difference between discount rate and interest rate. They're not the same thing. They're very likely very similar because future value and present value are similar too. So they have similar value, but normally discount rate is slightly lower because the future value are normally higher than the present value. So the interest rate is higher, discount rate is smaller. Any question? Are we okay? So we have similar formula. We also have the dn, like before we have in. In is an minus 1 divided by an minus 1, because for interest rate, you have future value minus present value divided by ending value minus beginning value divided by the beginning value. For interest rate and discount rate, you have ending of the interval, and the nth interval is n minus 1 to n in that time frame. So you divide by an will be the ending value of that interval. Any question? Are you okay? So kind of have this kind of differentiate the discount rate from interest rate, even though they should have similar value. All right, let's look at an example if we have time. All right, so we have, maybe we finish this example, a rate of interest and the rate of discount are said to be equivalent for an interval if for each $1 invested at time 1, the two rates produce the same accumulated value at time 2. So basically we say you may have interest rate and discount rate, and for the same time interval, and if they're for the same time interval and the same cash flow or same future value, same present value, you can calculate interest rate and discount rate for the same cash flow. They may be different, but they are considered equivalent. I hope that can make sense. So as long as they're talking about the same thing. More generally, two different methods of specifying investments growth are called equivalent if they correspond to the same accumulation function. So if you draw the timeline, you draw the value on the timeline, if they're pretty much the same, then they are equivalent. So this, and we often have to calculate for a particular cash flow, what's the discount rate, what's the interest rate. All right, so this is really about the relation between the two. Okay, so for T1 to T2, assuming that the I T1, T2 is the interest rate, D T1, T2 is the discount rate. So if you are calculating the future value for that time frame, it will be 1 plus I T1, T2. That's how many grow from 1 to that future value. And then what about the 1 minus D? 1 minus D allows you to go back. That's why it's called discount. A discount rate allows you to figure out from a future time point back to the beginning of that time frame, what will be the value. So you increase to I plus 1 plus I, and then you discount back with 1 minus C multiplied, and you're back to 1. So essentially these two are reciprocal of each other. 1 plus I allows you to grow to the end of the time point, and 1 minus C multiply 1 minus B allows you to go back to the beginning of the time, that time interval. All right, this is really a K equation, allows you to equivalently change from D to I to D. And then you multiply, expand the right side equation 1 times 1. I times 1, 1 times D, I times D, and you end up with the same equation. The 1 can be canceled, and we get this equation from either one of this equation. If you follow using the interval T1, T2, it's a little cumbersome to write. Instead, we can write I n, or we can just get rid of the n, and then we have 1 plus I times 1 minus D equal to 1. From there, that allows you to simplify the relation. So bottom here, I like this pair of equation rather than the left side pair of equation. Left and right, they're very similar, but the one on the left is really lengthy to look at. They're pretty much meaning the same thing, right? Essentially, we're saying I and D are very similar. The only difference you have to adjust. You want to make the D slightly bigger. How can you make a number bigger? You divide it by a number slightly less than 1. So we're enlarging the D to the point equal to the I, or you can make the I smaller to reach D. How do you make it smaller? You divide it by 1 plus I. projected back onto D. So these are the conversion from D, you can calculate I, and from I, you can calculate D. So the bottom right two equation is very useful whenever, sometimes we were given I, we want to calculate D, sometimes we were given D, we're trying to calculate I. So these are a useful conversion between I and D.
So much.
All right, I want to finish with this set of equation, especially the bottom two, it's the most useful one, since we do want to convert them. Okay, that will be for today. Please try the 1.5 homework. If you see any question, we can talk about it on Thursday. That will be it for today. Thank you. Okay. Hope it's not too much.
Better.